Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss steam turbines, use of horsepower valves and correct speed control. A steam turbine is a machine with an ancient genealogy. It is a direct descendant of the overshot water wheel, used to kick off the Industrial Revolution in England, and the windmill still used in Portugal. Turbines are widely used in process plants to drive everything from 2 horsepower pumps to 20,000 horsepower centrifugal compressors. They are versatile machines, in that they are intrinsically variable speed devices. Electric motors are intrinsically fixed speed machines. It is true that there are a variety of ways to convert AC, alternating current, motors to variable speed, but they are all expensive and complex. There are 2 general types of steam turbines, extraction and condensing. The most common turbine with which the process operator comes into contact is used to spare an electric motor-driven centrifugal pump. The 3-phase AC motors used in the United States and South America are either 1800 or 3600 RPM. The motors used in Europe are 1500 or 3000 RPM. Small steam turbines, 20 to 500 horsepower, used to drive centrifugal pumps are rated for the same speed as the electric motors that are used in that particular service. Principle of operation and calculations. Did you ever turn a bicycle over on its handlebars and squirt water from a garden hose at its front wheel? What causes the wheel to spin with such great speed? What is the property of water striking the spokes that causes the wheel to spin? Is it the pressure of the water hitting the spokes that spins the wheel? Certainly not. While the water pressure in the hose might be 40 psig, as the water discharges from the hose nozzle, its pressure surely falls to the atmospheric pressure in our garden. But what happens to the pressure of the water? It is converted to velocity. It is the velocity of the water, then, that causes the wheel to spin. The velocity of the water is transferred to the spokes of the wheel. What force of nature causes a windmill to spin? Answer is, the wind, or the velocity of the air. What causes a steam turbine to spin? Answer is, the velocity of the steam hitting the turbine wheel. A simple steam turbine. Shown in picture is a conceptual drawing of a simple topping steam turbine. An actual turbine does not look anything like this sketch. The 400 psig mode of steam enters through a governor speed control valve. This valve, sometimes called the Woodward governor, controls the flow of steam into the steam chest. If the turbine is running below its set speed, the governor valve opens. It is really just like cruise control on your car. You select the speed you want to drive at. If the car is going slower than the speed you selected, its set speed, the gas pedal is depressed to bring the car up to your selected set speed. The governor speed control valve is just like the gas pedal. The pressure drop across the governor control valve as shown in picture is 100 psi. This sort of pressure drop is called an isothalpic expansion, a term used in thermodynamics meaning that the heat content of the steam has been preserved during its reduction in pressure from 400 to 300 psig. It is also an irreversible expansion, meaning that the ability of the steam to do work has been reduced. As the steam passes through the governor, a substantial amount of its pressure is lost, because of friction in the governor valve. The 300 psig steam next passes through the steam nozzle. This is an ordinary nozzle. It screws into a hole in the wall that separates the steam chest from the turbine case. The nozzle is shaped to efficiently convert the pressure of the 300 psig steam to velocity. The pressure of the steam, as soon as it escapes from the steam nozzle, is already the same as the exhaust steam pressure, 100 psig. All the pressure energy lost by the steam in expanding from 300 to 100 psig is converted to velocity. This is called an isoentropic or reversible expansion. The term isoentropic is a thermodynamic expression meaning that the entropy of the steam has not increased. The term reversible in this context means that I could take the high-velocity, 100 psig steam exhausting from the nozzle, run it backward through an identical nozzle, and convert the steam's kinetic energy back into 300 psig steam. An isoentropic expansion is also frictionless, in that the ability of the steam to do work is preserved. If you are using your Mollier diagram, you will have noted that the temperature of the steam has dropped from 375 degrees Fahrenheit to 220 degrees Fahrenheit. The 220 degrees Fahrenheit is the temperature of 17 psi as saturated steam. That 155 degrees Fahrenheit drop in the steam temperature represents 85 BTU per pound. The 85 British thermal units, BTU, has been converted into kinetic energy. Most of the kinetic energy of the steam, as it passes through the steam nozzle, is derived from the temperature of the expanding steam. The high-velocity steam strikes the buckets around the rim of the turbine wheel as shown in picture. Actually, these so-called buckets resemble blades or vanes. I imagine the term bucket is a carryover from the days of the water wheel. The velocity of the steam is now transferred to the spinning turbine wheel. If the turbine is running below its set speed, the speed controller causes the governor speed control valve to open to allow more steam to flow into the steam chest. Calculating work available from motive steam. Dear engineers, please recover from your desk drawer your steam tables. In the back, there will be a Mollier diagram for steam. This picture is a representation of your Mollier diagram. We will use this diagram to calculate the amount of work we can recover from steam with a turbine. 1. The motive steam conditions are 375 degrees Fahrenheit and 160 psia, which determine point A. Note that the motive steam pressure is the pressure in the steam chest, not the supply steam pressure. 2. When steam passes through a turbine, it undergoes an isoentropic expansion. The work that the steam does in transferring its momentum to the turbine wheel exactly equals the shaft horsepower developed by the turbine. The entropy of the system is therefore constant. On this basis, extend a line through point A straight down the Mollier diagram. This line represents a constant entropy expansion. 3. The exhaust steam pressure is 17 psia. The intersection of the isoentropic expansion line and 17 psia constant pressure line together determine point B shown in picture. 4. Now measure the enthalpy difference in British thermal units per pound of steam between points A and B on the vertical, y-axis, scale. 5. As we shall see in the following section, most of the increase in velocity or kinetic energy of the steam does not come from the pressure of the steam, but from its enthalpy. By enthalpy, I mean both the temperature and latent heat content of the steam. Thus, as steam expands through a steam nozzle to a region of lower pressure in the turbine case, the steam cools and is partly condensed. 6. Divide your answer by 2500 BTU per horsepower. This is the fraction of a horsepower that each pound of steam can produce. However, as turbines are not 100% efficient, multiply the calculated horsepower by 0.90 to account for internal turbine inefficiencies called windage losses. Incidentally, the reciprocal of the calculated horsepower per pound of steam is called the water rate, which is the pounds of motive steam needed to generate 1 horsepower worth of shaft work. 7. Multiply the horsepower per pound of steam calculated in step 6 by the turbine steam flow in pounds per hour. This is the total shaft work that appears at the turbine's coupling. This is the amount of horsepower that is available to spin a centrifugal pump or a variable speed air blower. Exhaust steam conditions. You may have noticed that point B in picture is below the saturated steam envelope line. Does this mean that the exhaust steam would have appreciable amounts of entrained water? Does this mean that the motive steam may sometimes partially condense inside a turbine? Answer is yes. Does this also mean that turbine exhaust steam may have too high a moisture content to be used in certain downstream services? Well, it is fine for reboilers, but it would be unsuitable for steam jets. Looking at picture, see if you can agree with these statements. The higher the motive steam superheat temperature, the drier the exhaust steam. The higher the exhaust steam pressure, the drier the exhaust steam. Lowering the exhaust steam pressure always allows us to extract more work from each pound of steam. That is why we often exhaust steam to a condenser. But other than minimizing the exhaust steam pressure, how else may we increase the amount of work that can be extracted from each pound of steam? Horsepower valves. It is the velocity of the steam impacting on the turbine wheel buckets that causes the turbine to spin. If that is so, then the way to extract more work from each pound of steam is to increase the velocity of the steam as it escapes from the steam nozzle, as shown in picture. The escape, or exit, velocity of this steam is a function of the steam pressure in the steam chest. If we raise the pressure in the steam chest by 30%, then the velocity of the steam leaving the nozzle would go up by 30% as well. It is true that I could simply open up the governor and reduce the pressure drop of the steam across the governor from 100 to 10 psi. This would raise the pressure in the steam chest from 300 to 390 psi-g. But I would also get 30% more pounds of steam flow through the nozzle. The turbine would spin a lot faster and develop a lot more horsepower. This is not my objective. What I wish to achieve is to maintain the same horsepower output from the turbine. At the same time, I want to force open the governor speed control valve, raise the pressure in the steam chest, but decrease the steam flow through the steam nozzle. The only way this can be done is to make the nozzle smaller. We could shut down the turbine and unbolt the steam chest to expose the nozzle block, which is the wall that separates the steam chest from the turbine case. We could unscrew the existing nozzle and replace it with a smaller nozzle. A nozzle of 20% less diameter would reduce the nozzle cross-sectional area by 36%. 1.00 minus 0.20, power 2 is equal to 0.64 equals 64%. 100% to 64% equals 36%. This procedure is called reducing the port size of the nozzle. It works fine, except that we have permanently derated the capacity of the turbine by 36%, and next month we might need this capacity. Speed valves. This picture shows a steam turbine with 3, rather than 1, nozzles. The single, largest, left-hand nozzle is called the main nozzle. It handles 60% of the motive steam flow. Each of the two smaller nozzles handles 20% of the steam. These 20% nozzles can be plugged off by a device sometimes called a horsepower valve, jet valve, speed valve, star, for the handle shape, valve, or port valve. If we close off one of the two horsepower valves, steam flow into the turbine will drop, initially by 20%. The turbine will slow. This will cause the governor valve to open. The pressure drop across the governor will decrease. The pressure in the steam chest will rise. The flow of steam through the 60% port nozzle and the remaining 20% port nozzle will increase. The velocity of the steam striking the buckets will also increase. The turbine wheel will now come back up to its set point. The net effect of this exercise will be to save not 20% of the motive steam, but 10%. The 20% reduction in nozzle area is partially offset by the opening of the governor valve. The inefficient, irreversible isothalpic expansion and pressure drop across the governor speed control valve is reduced. The efficient, reversible isoentropic expansion and pressure drop across the nozzles is increased. If we now attempt to shut the second horsepower valve, we may be able to save a second 10% increment of steam. But if the governor goes wide open, we will have to open this horsepower valve again. You see, once the governor is 100% open, we will have lost our ability to control the turbine speed. This is no good, because we want the turbine to run at a constant speed. Do not pinch on the horsepower valves. They must be left completely open or firmly closed. Leaving them in a partially open position will badly damage the valve seats by erosion, reduce the efficiency of the turbine, and make it impossible to close the valves in the future. Selecting optimum turbine speed. An ordinary American-type turbine is designed to run at 3,600 RPM. Its overspeed trip will cut off the motive steam flow at about 3,750 RPM. But the turbine can be run at any lower speed. There is usually a small knob on the left side of the governor valve assembly that is used to change the set speed. The question is, how do we know the best speed to operate the turbine? This picture shows a centrifugal pump driven by a steam turbine. The correct operating speed for the pump and turbine is the speed that puts the process control valve in a mostly open, but still controllable position. As we slow the turbine to force open the process control valve, the turbine's governor valve will close. Steam flow to the turbine will decline in accordance with fan laws. Shaft work is equivalent to cube of speed of driver. This means that if we drop the speed of the turbine by about 3%, motive steam flow will decline by about 9%. However, there is an additional benefit. Slowing a turbine closes the governor valve. This may now permit us to close an additional horsepower valve without losing our flexibility to control the speed of the turbine. Closing that final horsepower valve will save us another 10% of steam. Our overall objective is to wind up with both the process control valve downstream of the pump and the governor speed control valve in a mostly wide open, but still controllable position. To achieve this dual objective, we have to simultaneously optimize the turbine speed. Optimize the number of horsepower valves that are closed. It is rather like solving two equations with two unknowns. An old, but better, idea. The control scheme shown in picture is certainly quite common. But is it the best? This picture is a copy of the crude charge system in a now-defunct refinery. It worked fine. The required flow of crude directly controls the governor. The turbine speed is then always at its optimum. The delta P across the process control valve is always zero, because there is no process control valve. This design is a direct descendant of the original method of controlling the steam flow to pumps. The steam inlet valve was opened by the operator, so that the desired discharge flow was produced. Why, then, do we need process control valves on the discharge of variable speed-driven pumps? Why, indeed. Steam rack. On larger steam turbines, we have automatically, rather than manually, operated horsepower valves. The mechanism that controls the movement of the horsepower valves is called a steam rack. If you have a large steam turbine driving a compressor, you have likely seen such a steam rack. A horizontal rod extending across the width of the turbine has a half-dozen cams fixed along its length. These cams lift and lower, in sequence, plungers attached to the horsepower valves. Watch these plungers in action. If you slow the compressor, here is what will happen. 1. The governor valve will start to close. 2. The steam chest pressure will fall. 3. The steam rack will move, so as to close only one of its multiple horsepower valves. 4. The steam chest pressure will rise, and the governor will open back up. If you look on the local control panel of such a turbine, you will probably see 4 steam pressures displayed. Steam header pressure. First stage steam chest pressure. Second stage steam pressure. Exhaust steam pressure. These larger turbines often let down the steam in 2 or more stages. They are called multi-stage turbines. Their principle of operation is not significantly different from a simple single-stage machine. Condensing turbines. Most of the turbines you will encounter in your work are called topping, or extraction, turbines. The idea of such a turbine is to extract much of the potential work from the motive steam, and then use the exhaust steam to reboil towers. Typically, the energy content of the exhaust steam is only 10 to 20% less than that of the motive steam. That is the calculation we just did with the Mollier diagram. The rest of the energy of the steam may then be used as the steam condenses to reboil towers. This sounds pretty efficient. It is the basis for the new cogeneration projects you may have heard about. Of course, this system was used by the British Navy in the 19th century. The condensing turbine does not produce exhaust steam. All the turbine exhaust steam is turned into water in a surface condenser. We will learn surface condensers in next video. The surface condenser is just like the sort of vacuum condensers we discussed in another lecture. The exhaust steam condenses under a deep vacuum, typically 76 mm of mercury, or 0.1 atm basically. Then, a condensing steam turbine loses all the potential benefit of using its exhaust steam to rev oil towers. But for what purpose? Let's say a turbine was using 400 psig or 415 psia steam exhausting to a 30 psig or 45 psia steam header. The work generated was 2000 horsepower. If we had condensed the steam at 76 mm of mercury or 1.5 psia, the work generated would be 4000 horsepower. In the first case, the delta P of the steam was 370 psi, 415 minus 45 is equal to 370. In the second case, the delta P of the steam is 413.5 psi, 415 minus 1.5 is equal to 413.5. If the delta P increases by only 12%, why does the amount of work that is extracted from each pound of steam double? The answer is that it is not the pressure of the steam that drives the turbine. It is the velocity of the steam impacting on the turbine wheel buckets. The velocity of the steam escaping from the steam nozzle as shown in picture is 25 feet per second, when the exhaust pressure is 30 psig or 45 psia. What, then, would be the velocity of the steam if the exhaust pressure were 76 mm of mercury or 1.5 psia? 25 feet per second times 45 psia divided by 1.5 psia equals 750 feet per second. No wonder the work we can extract from a condensing steam turbine is so much greater than with an extraction, or topping, turbine. The most efficient condensing turbines may convert 30% of the steam's energy into work. These turbines use 1500 psig steam and exhaust to a surface condenser at 50 mm of mercury. The most efficient machine ever built is the high-bypass, radial flow jet turbine engine, commonly used in commercial aircraft, which has a 40% efficiency. I rather like to adjust steam turbines. It is just nice to see how the second law of thermodynamics functions in the real world. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.